So today we are happy to have Alyssa Renata from Imperial College London, who will speak about the game spectrum of a monad. Please go ahead.
Thank you. Um, I should also say that it'll be nice to just take questions along the way because I don't want to talk for 50 minutes straight. Um, anyway, so there's going to be two parts to the talk. Um, and in the first part, there won't be that much games, but I will lay out the sort of the failure conditions which motivate why we want to talk about games. Um, so essentially, the first part of the talk is going to be about this adjunction. Um, on the left side, we have just monads on set. And we think of these as representing like experiments or computations in the sense of Plotkin, Power, and Moggi. Um, Now, the idea here is that your computation might interact with the environment along the way as it does its computation. And so the thing on the right side here is essentially the representation of that environment. At least that's the intuition. So we represent the environment as a stateful system. So the objects are small categories, and an object of one such small category is a state of the system. And a morphism of one such small category is a transition between states. So really, when we say small categories here, we're thinking of transition systems. But then the weird bit is that the morphisms that you get are not functors like they usually are, but they're these things called retrofunctors or cofunctors. If you've seen them, you know what they are. If you've not seen them, I'm going to define them in the next slide. Um, anyway, so the idea is that you should think of this as some sort of duality result or dualism. So the analogy that you want to have, for example, is between commutative rings and affine schemes, where you think of your commutative ring as a ring of measurements or functions on some space, and then the construction of the affine scheme corresponding to that ring exactly reconstructs the state space from which you're measuring. Um, if you're not familiar with this, another example that you can think of is the duality between Boolean algebras and stone spaces. Um, and here, the Boolean algebras you can just think of as binary functions, essentially, elements of the Boolean algebra. Um, now, the nice thing about these two things are that they are actually dualities, so you get an equivalence. But this thing is very much not an equivalence. So actually, the problem is that if you take the left adjoint applied to some monad, for a lot of monads, it's often trivial. So you don't faithfully represent the monad by the sort of stateful environment that you reconstruct from it. So this is kind of problematic if you want to sort of push this analogy further, for example, to develop some sort of scheme theory. Um, so the idea is that in the second half of the talk, after I introduce this adjunction, we'll be replacing the category retro with the template games that Paul-André Melies introduced in order to model linear logic. Um, the idea being that a lot of the structure of the environment that you reconstruct from the monad actually falls out of a game that you can construct from the signature of the algebraic theory generating that monad. Um, at least that sort of works for signatures alone, so without accounting for the equations in the theories. Um, and then at the end of the talk, I'm going to sort of um, remark a little bit about how we can deal with the equations, but it seems like quite an annoying problem conceptually. So that's kind of the plan for the talk. I'm going to talk about the adjunction um, with an eye towards why it doesn't really work that well. And then I'm going to talk about how we can start working to solve the problem using games. And then I'm going to end with a lot of question marks for the talk. So this is about this left adjoint that I presented before. So it's called the behavior category. But to better understand the construction, it's better that we look at the right adjoint first, which is also easier to introduce. Um, so the right adjoint is called this global sections functor. So the idea is that you're given this small category C. The global sections functor constructs the monad, which given a set A, basically just takes the um, essentially you look at index sections to the source map. So you're looking at maps from assigning to each object a morphism along with some return value. So there's some transition out of that state. And then you need to enforce that the transition, the domain of that transition is actually the state that you started with. And that's represented by the square. Um, but the picture that you have is inside the category. It looks something like this. So to each state, you just sort of take a motion out of that state or a transition. So it looks like the sort of Brownian motion pictures that you encounter in high school. So you can kind of think of it as a monad of Brownian motions. Um, a special case that is very instructive, I think, is you fix some set W and then you construct the co-discrete category out of it. That just means that you can, from any state, transition to any other state uniquely. And then if you construct the global sections monad out of this category, then you get maps from W to the starting W and the target W. But since the starting W is forced to be this one, as enforced here, you actually have no choice in this side. So you end up with just maps from W to W times A, and this is commonly known as the state monad. Yes, I think Marcelo has a question.
Hi, I just want to ask you, uh, just to understand a little better what this gamma of C is the
Mhm.
Kleisli of this monad the same as the arrow category of C?
Um,
If you know.
Not off the top of my head,
Okay,
but
it's okay, no worries. Thank
if
you.
you think it checks out, then might be true. Um,
Okay, thank you.
yeah. Um, I'll let you figure it out and then you let me know if it's true. Um, so yes. So in some sense, this global sections monad is just a very fancy state monad where you not only keep track of where you send your state to after the computation, but you also keep track of the sort of transition that you take in order to reach that new state. Um, yes. Now, here, now that I've introduced this gamma, I can sort of explain why the morphisms are not functors. Essentially, it's because the objects occur contravariantly, whereas the transitions occur covariantly. So you kind of want to plug in something contravariant here, um, and then something kind of covariant here, um, just in order to exploit this map by precomposition and postcomposition. So this thing comes from some D0, which we have here. So you send objects one way, and then you want to send transitions the other way. But the way you do it is that your starting data is you start from somewhere in D, and then you send it sort of backwards on the object side. And then given any morphism coming out of that thing, you want to send it forwards to some transition in D that kind of simulates that transition. So you can kind of think of this as a simulation, a forward simulation. Um, so that's kind of why we don't really want to work with functors here. Now, actually, we can already from this alone work out some of the failures of the left adjoint. So here's a bad example number one. Suppose the monad that you care about here has a nullary operation. Then let's just look at the sort of the state monad. So you plug in a co-discrete thing here, and then you look at all the maps from this T into that. So we're looking at maps of this shape. Now, we basically have to send the Z into a map that goes from W to W times the empty set. But essentially, there is no such map unless W itself is empty. So this already tells us that there's not very many maps that exist here. So whatever this thing is has to be very degenerate. And then the bad example number two also hits something that I think occurs very commonly in monads. So just assume you have some binary operation. Then you chase out what you need, and you essentially come to having this map W to W times 2. But then you require it to respect this map, which basically says that whatever I send this state to, you get another state and some value like 0 or 1. And then if you flip that value, that has to be the same thing. So in other words, as soon as you have some state, you demand that 0 equals to 1, which is a contradiction. So again, you need that there be no states in the first place. So from this, you can kind of essentially infer that the only sensible choice for the left adjoint is to plug in the empty category. And I'm also going to keep something from this for later. So I'm going to make this definition now, but it's not going to come in until a couple more slides. But this pattern actually occurs very commonly and was defined by John Power and Olha Shklarowska in 2004. So the pair of a set W along with this map into the global sections of the codiscrete of W is what is called a co-model, because you can kind of think of it as just fixing a set of states, and then this map tells you how to run the computations in your monad or the elements of your monad as functions from W to W times blank. So just transitions in that state system. And then the morphisms of co-models are just the maps from some W to some other W prime that commute appropriately with this map. So now we're in the position to talk about the left adjoint. Essentially, we have to work kind of from a systems perspective here. So we think from the perspective of either the program or the environment. So here, from the program's perspective, if the system is in some particular state C, then essentially the observable behavior of this state from the program's perspective is that it tells us how to run this term, right? So you make this transition inside your system and you end up in some C prime, so that's this bit, but you also get some value A. And this value A, if you think of the term as some syntax tree, is essentially a leaf of the tree. So it literally tells you how to run down the tree. So the objects of the behavior category are just going to be precisely these observable behaviors. So ways of running down terms down to the leaf, or in other words, natural transformations from the monad to the identity. Now, the thing is, this is not going to be a monad map, but it's going to respect, you're going to have to force it to respect this sort of condition, um, which basically says that if you take a composite, so this is just the Kleisli composition. So the picture that you have is something like this. So this is like a U1, U2, U3, U4. Now, if I apply this behavior to this composite, then I end up down here, and so I end up going into U2. And then what this says is that this has to be the same as running. So this thing says that this is T, but I systematically replace all the other U's by U2. So what this basically says is that I've run it down into U2 and I don't care what happens in all the other trees. So I can basically sub in whatever I want. Um, so that's the sort of condition that you need. Now, if we want to talk about the morphisms, we need to switch perspectives. So now we're talking about from the system's perspective, about distinguishing the computations that are run on it. So you're in a particular state C. Now, if I run T and T prime, and they both induce the same F, like this sort of F here, then from that particular state's perspective, the two computations are indistinguishable. So what we're going to do is from a particular state or from a particular behavior, we're going to take all the computations and kind of quotient them by this observability. Now this thing is a bit annoying to describe, so I'm not going to describe it in general, but when we work out the examples, I'm going to explain how it works. And we also, because we only care about the transition, we don't need to care about what return value pops out. So we suffice to take the unary computations. So a generic element, a generic morphism looks something like this. So this is an equivalence class of some element of the monad. And then you basically go from some observable behavior into the observable behavior where you do the computation that you're talking about first before doing the thing that you actually want to run. So this thing is the same operator as here, which is the thing where you sort of replace all the subtrees by a particular one. So let's just work out an example. The simplest possible example is you just take the free theory generated by a single binary operation, which computationally you can think of as like asking for the result of a coin flip. And so here's an example tree that we're going to look at. Now, the point is that if I try to run this thing with respect to a particular behavior, we find that the behavior is determined by what it does on some very standard looking trees. So by systematically invoking this sort of admissibility condition that I had previously for the behavior, like here, if I know that it's going to give me the right side of the coin flip, so this bit, we're basically inspecting this bit, and it's going to give me 1, then I get to replace the left tree by the right subtree. So it looks something like this. And since these two are the same, I might as well simplify my notation to look like this. And then we're going to do the same thing again with this bit. But now don't forget that we have to first ask what it does on this transition, followed by this. So again, we can inspect what it does on this B followed by B. And if this time it gives back 0, then we pick the left subtree. So we take this one and we sub it into here. And you do the same thing again, and again, until you eventually reach something of this form, right? So just a sequence of B's followed by a particular leaf that has been duplicated everywhere. So it's like a complete binary tree. And then at this point, you can apply the naturality essentially to conclude that it has to return this A2. So the behavior is essentially determined by what it does on all these trees of standard form for every natural number n. So you're just sending each natural number to the result like 0 or 1. So in other words, infinite binary streams. Um, so you can kind of think of this as like a particular infinite binary stream is the result of every coin flip that will ever happen from that point on. Now I have to explain what the quotienting that you do to get the transitions. Um, so let's say we have these two trees, and we're going to look at this particular beta that had these that were determined by this data. Then essentially what the quotienting says is that you ignore the parts of the tree that you never explored using beta, and you simply look at the sequence of operations that you traversed. So in this case, these two trees, you end up traversing the same sequence. So you end up identifying them. So in other words, the equivalence classes of this equivalence relation are going to just be the natural numbers in this case, because you're just counting how many bees you see along the way. So essentially, the set of morphisms of your category looks like the set of states. And then for each of those states, you append sort of all the possible natural numbers. So all the possible transitions or coin flips that you do from that state. So the generic element looks like this, where out of a particular infinite binary stream, if you're taking, say, like the transition 3, then you're doing 3 coin flips. And so you're consuming the first 3 binary digits of your infinite binary stream. So you're taking the rest of the binary stream as the new state where you transition to. Now we can generalize this to free theories or like arbitrary signatures. The basic idea is the same, but now it's a bit more convoluted. So if you're at a particular state, then you have to include the data of basically given each operation, what sort of return value you're going to give for that operation. And that return value is going to be taken from the arity of each of those particular operations. And then depending on what operation the program actually invokes, you're going to transition to different states. And that's what you represent with this. So you basically take your behaviors to be these infinite trees where the branching is determined by the number of operations. And the transition that you take for a particular operation is just going down that particular branch. And so earlier we had that the transitions were the natural numbers because we were just tracking the number of binary operation that we encounter. Now we have more than one operation, so we have to keep track of the data of all the operations that we encounter along the way. So it's just a sequence of the operations that you encounter. I'm going to focus on the free theories because of the next part of the talk. But we all can also compute other examples. So if you take the state monad, then your behavior category just ends up being this co-discrete thing on the set of states. And then the other interesting thing is that you can construct this monad of partitions for a particular Boolean algebra. And then your behaviors end up being the discrete category on the ultra filters of that Boolean algebra. Now, there's in fact a topology that you can put on this naturally, which ends up giving you the stone space corresponding to that Boolean algebra. So in our paper, we also did the topological and in fact the localic version, which generalizes stone duality. But my relationship with topology is currently complicated, so I'm not going to talk that much about this. And anyway, this version is already sufficient to sort of see the failure. And this doesn't fix that failure, which is the stuff about this commutative binary operation and the nullary operation business that we had earlier. So now that's what I'm going to talk about,
Sorry
is
to
how are we
interrupt.
going to,
In the case of power
yeah,
set and finite power set, how does it look like?
so both of those run into the commutative binary operation.
Right.
So you get that the behavior is the empty category.
I see. Thank you.
Which is so that's like the problematic thing about the two counter examples that I had earlier is that they kill like 80% of monads, I guess. I mean, there's infinitely many, so I can't really give a number, but the ones that you encounter in
Right.
practice often die when you apply this,
Okay.
basically. Hmm. Um, so this is all about fixing this, but the idea that we're going to do is that we're going to basically generalize um, the behavior category to games. And the starting observation is that so far, the way I've described the behavior category is very interactive. We're always talking about this interaction between the program and the environment. So the idea is that we should just formalize this and construct the sort of game in which this interaction is happening. So here's a sort of example with our most baby version, where we just take this single binary operation. Um, so I'm going to construct this alternating two-player game. And the nodes represent positions, and the edges represent the moves that you can take. And here, the color represents who is taking that move. So in particular, the red the red is the program, and the program can take basically two possible moves. It could request data from the environment, or it's decided that it's finished, and it could just give back the return value that it wants. So this is where the set A comes in. So for each element of the set, we add a transition that represents the exit with that particular return value. But now if the program does ask for data, the environment can respond. And in this case, the two possible responses are with the 0 or the 1, which comes from the arity of the operation. Now, if we look at the winning strategies for the program, then they look something like this. To be less boring, we're going to do some actual interaction. So let's say the program asks for a particular re return. It asks for a particular element from the environment. Now you have to account for both possibilities of the environment returning 0 or 1. And so let's say in case it returns 0, you still ask for more, and also the same thing when it asks for 1. And then so on, you can fill out this tree and describe some sort of strategy. And the winning just means that you eventually have to exit in this case, because we're going to say that winning means that or losing means that the particular player who is to play has no moves to play. So that's true in this particular pool here. Now, if we look at what winning strategies look like in general, like for example, this one, that really is just the sort of syntax tree um, that you generate from their signature. So if you look at the winning strategies for the program in this game, then you get exactly the result of the monad applied to A. Now, if we look at the winning strategies for the environment, you have to account for the two possible plays of the program. And in the case that it exits, then you're just kind of screwed. So we basically have to look at the case where A is the empty set. So this is a bit dodgy, but let's just do that. But in that case, then essentially the data of your winning strategy, I mean, you can't really win in this game actually. So the best thing you can do is to just prolong play infinitely as long as possible. So your your strategy will be to always try to respond to a particular request for data with a 0 or a 1. So we get that the sort of winning strategies for the environment corresponds to the infinite binary streams in the case where we take A to be the empty set. Now, if you take a winning strategy for the environment and you take a strategy for the program, then that allows them to interact with each other. So you get a particular play that arises from those winning strategies. And that play is just the sequence of moves that are taken when both of the players use the particular strategy we've fixed. And if you think about what that play looks like, then it's exactly the data of the transitions of the behavior category. So it's this like sequence of operations that were played along with the final return value that you get at the end of the play. So an alternative way to describe the HOM sets of the behavior category is to look at all the possible plays that can result against the winning strategies of the against winning strategies for the program. Now, I think this is not my original idea, but I found it in this paper by Jeremy Koenig, although he was using a different sort of framework for games. But then I also talked with Richard, and apparently this was also worked out by Richard and Soichiro at some point. And then it sort of never materialized, but I'm just going to credit them here. So here's the idea in general. The game has a particular blue state here in which the program is to move. And from that state, for every operation in your signature, you add a move into some fresh state. And also for each of the sort of exit variables, you add one transition out of that. And then from that fresh state of the particular operation, for each of the arity, for each element of the arity of that operation, you add a transition back into the blue state. So we've already seen an example of this just before, and this is just a generalization. So the idea here is that if you have this sort of nullary operation in your signature, then we've already seen that you get no behaviors. So that essentially gives you an exit state sort of independently of these things, which means that the environment will always lose and cannot prolong play infinitely even. So you get a trivial behavior category, but the point is that the game itself is not trivial. So the idea here is to try and use the games as a sort of more primitive structure from which the behavior category falls out. And so it may happen that the game is not like well pointed, so you get trivial behavior category, but still the game represents some non-trivial interaction. Now, I guess the question is what happens with the equations. So I'm just going to say something very quickly here. I think at least for me, intuitively, what I want to do is to add two cells. So if I have the commutative binary operation here, I want to add a two cell that says that whenever the program plays B and then you respond with a 0, there's a two cell that says that you can always shuffle the history of the play so far so that it was as if this B was played and a 1 was returned. And then you look at all the behaviors that sort of respect this two cell, and in this case you get none. Here's a sort of picture of how I think about it. Is that you're playing the game on a two-sided board, and whatever you play on top dualizes on the bottom, and you can always flip the board whenever you want. But this sort of this sort of intuition doesn't really straightforwardly generalize. So at the end of the talk, I'll sort of say a bit more about this if I have the time. But the point now is that we want to at least like formalize this bit into some framework of games because there's very many frameworks of games. But here's sort of the most useless definition of games that I think you will encounter. Um, so you fix a category with finite limits, and then you fix an internal category in that category C. So this thing is called like the template for games. And then you immediately get a double category of template games as the sort of double slice of the double category of spans in that category C with respect to the template category, which you view as a monad in span. So in other words, a lax double functor into it. Okay, so this is a terrible definition because it really doesn't tell you any of the intuition. But in order to communicate the intuition, I think it's better we just fix a particular template and then sort of look into what it says. So the thing of interest to us is where C is the category of small categories. And then we're going to take this very small category of objects, which is generated by these two positions, which are called minus and plus. And then the nodes are going to just be these things called program and environment. So essentially what we're going to do is that we're going to define games as certain categories whose objects and morphisms are labeled by these things. And this is like the labels, basically. So we're going to label each position by its polarity, which determines who is to play. And we're going to label each morphism as a move. So whose move does it belong to? And then we're going to have also for the category of morphisms, this sort of thing. So this represents the sort of labeling that you do when you're playing a game on two fronts. So this is a kind of picture that you want to have. This is me or you, I don't know. So you have the target game in which you play the environment. So that's this bit. And then you have the source game in which you play the program. So what you're trying to do is that you're trying to act as the environment in one game, but you're using the other game as a resource in order to become the environment in the other game. And this sort of labels the four possible moves that can happen in this configuration. Now, supposedly, I also have to describe what the identity and the composition for this internal category looks like. But it's a bit annoying and I'm not going to use it that much. So instead, you get cool pictures which represent the identity and the composition. So the identity is just this sort of copycat strategy thing where essentially you say you're fighting two very smart chess players, but you are very stupid. But there's actually an easy strategy which you can do, which is just whatever move one player does on one side, you use that, you play the exact same move on the other side. So I think this is a like representative example of what I mean to use one game as a resource to play the other one. And then the composition looks something like this, where there's two of you and you're playing this game on two sides, but you're also sharing a game through which you can communicate. So what you do is you work together and use this game to communicate, but then you are doing this inside a black box, so you hide whatever happens inside here. Now, if you've seen the movie Pacific Rim, you get like these two pilots where they go into a giant robot and then they synchronize with each other and they fight giant monsters. So that looks like this. Uh, um, okay, so I hope that was a completely formal explanation of the
Great reference,
identity
by
and
the way.
decomposition. Sorry.
Great reference.
Thank you. Um, so the less useless definition is this. Um, so the objects of our double category are a small category along with a labeling functor into the category of objects. So this just tells you, this just labels the color of the objects and the morphisms. Now the type maps are not very useful actually, so I'm just gonna put them there. You can look at it. Um, the loose maps, though, they are the important ones. So they are the strategies. So these are the sort of spans of categories living over each of the game um, that has a labeling functor, but into the category of morphisms. So the strategy is a kind of, essentially the strategy itself is a game, but it's like a two-sided game. Um, and then the two cells are the sort of reindexings of the strategy games that make everything sort of commute. Um, so this is actually a very abstract definition, and it doesn't demand the sort of usual constraints that we want from a strategy, like that it's like winning or deterministic or even like responsive to particular moves. So it doesn't even describe who the strategy belongs to, for example. Um, so I'm still not entirely certain how you're supposed to um, enforce this, but since all you're using this for in the original papers is to construct models of linear logic, apparently this suffices, this level of abstraction. So in fact, because the type maps are really too tight, we're going to ignore them. So we're going to look at this by category of template games, where the maps are the strategies. Now we want to define a map from the signatures into games. We've already essentially described the game, so I'm not going to say much more about that. The colors that I used in the informal description represents the labeling functor, essentially. But then we should say what are the morphisms of signatures that we care about. And then the obvious one that we could use is like just the monad maps. Now, if we look at the monad map, so let's say that we have this particular monad map phi, and that phi on a particular operation sigma living in sigma 1 is this thing. So this particular tree where you use a bunch of sigma 2 operations. And then the leaves are going to be values that come from the arity of the sigma. Then essentially we're going to construct the game to look like this. So you have this unique plus plus state. And then each operation in sigma 1, you're going to add sort of one transition in the target game, something that does a transition in the target game. So we've gone from plus plus to plus minus. And then what we're going to do is we're going to use this to do some interaction in the source game. So we take this sigma 2 and we use this to describe this two-shot interaction where you ask for the particular value of the sigma 2 from the source game. So that puts you into minus minus. So I think it's good to remark here that you can think of this symbols as the health bar. If you're at plus plus and you're doing very well, but then here's an attack, so you lose one health. But then the analogy kind of breaks down because now you're doing the attack and then you lose more health. So it's a bit confusing, but something like this. So anyway, you ask for the value of sigma 2 from the source game, and then the source game tells you back one of the possible values, that's 0, 1, or 2. And then you sort of just keep filling out that thing following the shape of the tree. And then at the end, these things sort of represent your I1, I2, I3, I4. And so you can use that to transition back, because in the original game, in the target game, you still need to respond to this move. So this bit was invisible to the target game, but you still needed to respond to this particular thing. And that's what happens here. So that's the sort of game that you send a monad map to. But now there's also the co-models, which I from a couple slides ago. So just to remind you, these are the maps from T into the state monad on a particular set W. And now let's say that the particular interpretation at a particular state W is to produce the state W prime and this result I, which is a value of this sigma. Then you can also kind of model this by this sort of interaction, very short interaction, where in the target game, you're asked for the value of sigma at a particular state W. You immediately end up with the result, but also a new state W prime. So you can transition out of that back into this pool, into the new state W prime. So there's a common picture here where you have this fountain, which is very strong in its burst of water. But then the sort of pool is very meager. Or you can have this very big pool in the bottom and then a very sad tinkle out of it. So we want to have a common picture in which we have a big pool and a super powerful burst of water. Sorry, that was too colorful or flavorful. But this common picture on the side of the signatures essentially looks like this. So the maps are these things called residual co-models. And essentially the residual co-models are the same sort of thing as the co-models, but you're looking at state monad defined in the Kleisli category of some other signature sigma 2. So instead of W to W times the arity, you fub it by another signature thing here. And then you send this to the game where you kind of have this actual pool, and then you do the same thing where in order to interpret this particular operation sigma, you now do like the tree that you get here. That's this bit. But then at the end, you get not only the result of trying to evaluate this signature, but also the new state which you transition down into. So this is the common picture. And then this actually defines a monoidal pseudofunctor. So because this is a model of linear logic, you have a tensor. And here you want to take the coproduct of signatures, and you send coproducts of signatures to the tensor product of games, I think. I should say that, by the way, this is proposition, but the proof is very annoying, I think, so I haven't really written everything down. So take this with a grain of salt. And now, because I'm running out of time, I'm going to skip past this bit, but this is essentially about saying what the essential image of this functor looks like. And also about getting a sort of corresponding adjoint construction to this, because we want to think of this also as a certain kind of dualism or duality. And I think you need some kind of statefully indexed family of signatures. So I just want to make time to say something about the equations. So we said that we wanted to say these two cells. Now, Paul-André Melias actually knows already how to do this with two cells, where you sort of systematically replace the use of cat along with the Cartesian product by 2cat and the gray tensor product. But then if we try to work in this setting and we try to think about what to do for other sort of equations, like bxy equals bxx, it's not clear to me what two cell that you want to put, but it seems like the only sensible thing is to put the exact same two cell as bxy equals byx. But while this one selects for like no behaviors at all. So no behaviors satisfy this one. There is actually one behavior that satisfies this, which is the one that always spits back out 0. So the first idea that we have for dealing with this is to add some sort of silent transition, which happens to work, I think, in this particular example. So you mark applications of your 2-cell by a silent transition. And in this way, if you have this sort of behavior represented as a strategy, it won't have the silent transition, so it won't be touched by the 2-cell. So you can still keep this particular thing. But then it's not clear how to generalize this to other equations. And then in some sense, there's a lot of noise now because of this silent transition. The other idea is, I think, somewhat more radical, where actually you replace like 2cat by monoidal 2 categories. And the intuition or the idea here is that you view your signature actually as a tree computat, which generates a monoidal 2 category. And then you want your game construction to be a thing that polarizes this monoidal 2 category. So you take each sort of operation in your monoidal 2 category or in your computat, and then splits it up into 2 bits, which is the question and the answer bit. Now, because this is a monoidal category, your answer bit doesn't really split. So you just get a sort of monolithic thing that answers the question by sending it into 2 pluses. But if you now freely Cartesianize the thing here, then you are allowed to split this thing, and supposedly this picture should be somehow a shadow of this monoidal 2 category when you restrict it to generators or something like this. But this is also like very fresh stuff that I thought about yesterday. So literally no details other than what you see here. And then there is a bunch of future work, even more into the future work. And here's the references for the people in the recording. And thank you. Any questions?
Thank you very much. Are there any questions? If not, I have one. I think it's quite basic, but just to get the general picture. So what I'm used to is that the behavior in the case of the state monad is a coalgebra for the state monad. So the transition that you were describing in the pictures. But
Yes.
if we look at the category of comodels for the state monad, they are not coalgebras for the state monad. They are coalgebras for some comonad.
Yes,
a different
and
one.
this comonad is the dual of the
Exactly.
monad in a sense.
But my question was in the theory that you have, do you have anything that talks about the comonad of the state monad, which are
so
yes.
I think if you take the game and you dualize it, oh, Richard's already on and about to answer, I think.
Okay.
Okay. I think if you take the game and you dualize it, then this sort of corresponds to taking like the dual of the signature from which you generate it. So if you then generate the comonad from that dual signature instead, I think that should correspond to certain structures in the dual game, like strategies and whatnot.
But is there something about the coalgebras of the state monad?
I think not, because coalgebras for the state monad would sort of be like, it means you would already be on the environment side of things, kind of.
But
Whereas this
I
says that
think
you're on
I'm
the
misunderstanding the general picture. But for me, the coalgebras or the state monads are the pictures that you were drawing. So this is why I was a bit confused.
I guess they are, but it's like we have program and we have environment.
Right.
And if you take coalg of W times black W,
Right.
like at least the way we think about these things is that they actually already live in here. Whereas what we do is we start with a sigma that lives in here, or a t, and we're describing how to turn it into something that lives in here.
I see. But so before going to the game generalization, in the adjunction that you have, you are not talking about, I mean, the transition systems are not transition systems of the original monad. I think this
No.
is what I was confused. Okay.
Yeah. So
Okay.
if you take a state monad here, and you look at what pops out here, I mean, in this particular case, you will just get this codiscrete category on the
Right,
set of
right.
states from which you generate the state monad.
Yes.
So in a sense, the state monad already comes from here, right? That makes sense. So really, this state monad comes from a set that lives on this side.
Okay. Thank you. Are there any other questions? Okay. Well, if not, thank you again, Alyssa. It was very nice.
Thank you.